In this series of videos, we will be discussing the process of searching. Searching is the process of finding a target element within your group of items. That group of items is often called a search pool, and your group of items might be stored in an array or in a list or in some other data structure. And the idea is you want to find one particular target item within that group. The target may be in the pool, it may not be in the pool. Searching should tell you that, and it will also often tell you the location of that item within the pool. Now, we want to perform our search efficiently, and what that means is we want to minimize the number of comparisons we make. So every comparison we make obviously takes time. So an efficient search will make fewer comparisons. A less efficient search will make more comparisons. We always want to be reducing the number of comparisons we need to make, and that's what makes our search more efficient. In order to search, you have to have a way to compare items, right? So you have a group of items, you're looking for some target item, you're going to take that target and you're going to compare it to everything in your group. And so you need some way to do that comparison. And what this will typically be is it will be your overridden equals method. So for whatever class you're using that describes the objects you have in your collection, hopefully that class has overridden the equals method. That overridden equals method tells what makes two objects logically equivalent, and that's what will be used when you go through and compare. Is the target this item, yes or no? Is it this item, yes or no? Is it this item, yes or no? You'll use that equals method. There are other ways to compare. For example, if the class implemented the comparable interface, you could use the compare to method. But of course, not all classes do implement comparable, but all classes have an equals method because that equals method is inherited from object. So even if it's not overridden, every class will have an equals method. And that's typically what we use for search. Now, there are two main kinds of search. The first we're going to discuss is linear or sequential search. And after that, we'll talk about binary search. So for linear search, this is a search that begins at one end of your list or array or collection and examines every element in order and just keeps going, keeps looking, and it stops either when you find the element or when you reach the end of the list without finding it, meaning it's not in the list. Linear search is, as the name implies, linear in its growth efficiency. It's O of n. So if you think about that, that makes sense. Remember that linear growth means it's the solution time is going to grow at the same rate as the problem size grows. And if you're doing a linear search for an element on an array with 10 elements in it, you potentially might have to look through all 10 spaces to find it. If you double that and you look for an item in a 20 element array, you now have to look through all 20 spaces potentially to find it. So again, the solution time is increasing at the same rate as the problem size. So that's what makes it linear. So that is still pretty fast. You know, it's not quadratic or anything like that. It's linear. And again, you'll also sometimes hear this described as sequential search. Now, linear search, what's good about it is that it can be performed basically on any data, on sorted data or unsorted data. So sometimes you'll have an array or a list that is not sorted. You have to take a certain search approach if that's the case. Other times you'll have an array or a list that you know is already sorted, already ordered, and you can do different kinds of searches on that data. For linear search is nice because you can use it for unsorted data. There's no restrictions on the type of data that can be used for a linear search. But if it is sorted, if the data you're looking at is sorted, we can make the search a little bit more efficient, and we'll take a look at that. You can implement linear search either iteratively or recursively, and we're going to look at both. And linear search can work for arrays or also linked node implementation. So if you have an implementation that behind the scenes doesn't use an array, like the Java class array list, but instead uses linked nodes, like for example, the Java linked list class, linear search works for both. So it works for any of those different kinds of implementations. So let's take a look at the basic algorithm for linear search. And we're going to start off with the iterative algorithm. So here you might see that you assume that you have not found the element. So you create a Boolean, you say that it's false. The element's not in my list, and then you cycle through. Here we're assuming our data is an array, and I'm assuming it's an array of some kind of object. I don't even have to know what kind, but I basically just cycle through the entire array, and I say, hey, at any point, if my target equals that element, well, I found it, and I can set found to true, and then return true. If I go through the whole array and this conditional is never true, never executed, found will just remain false, and I'll return false, meaning it wasn't there. So this is your basic linear search implemented iteratively. You just look through the array or the list, elements in order, one at a time, comparing each one to the target. Now, we can actually improve this a little bit. So in this implementation, right, once we find an item, we find a match, we keep looking, right, because the loop is only going to stop when we reach the end of the array. That's how the loop is written. So that's potentially more work than we need to do, right? If we find our element in the first 2 items and there's 1,000 in the list, we don't need to look at those other 998 items, right? We can just end. So to do that, to improve this a little bit, and this is how you should use a linear search, we can add another condition into the loop conditional to check to see if we found it already. So now we're going to go through the whole array, but also only keep looking while the item is not found. So at first, when we get in here and initialize I to 0, let's say we have 10 elements in our array, so I is less than 10, and not found. So found is initialized to false, not found is true, so both of these together are going to be true. We'll go in, if the conditional isn't met, then found just keeps being false, which means not found keeps being true, so we'll just keep looking and looking and looking. But then, let's say we find our element, where target equals the element in our list, we reset found to true. When we come back up to check the next conditional on our next loop, not found will be false, so this whole condition will be false, and we will jump out of the array. So this allows us to not keep searching once we have found a match. Now, note that this means if you were looking for the index, if you wanted a position number of where an element is, rather than just true or false of whether the element is there, this would find the first index. If you wanted to find the last index, potentially if that item is in there more than once, then you would not be able to keep this part of the conditional. You'd have to drop that. Okay, so this is, again, improved. Now note, it's still O of n. So it has the same efficiency, the same order of growth as the non-improved version. But in the real world, this is going to be more efficient. So again, it's not more efficient from an order of growth, a big O perspective. Both the unimproved and the improved version are both order n, they're both linear. But in the real world, if there's a chance when you can only iterate 3 times, find your item and skip the next 1,000 iterations, you want to do that. So this is the better implementation to use. Again, if all you care about is just finding the first one or any one, and you're not looking specifically for the last one. Note that we could also just use a return here. We don't have to use a local variable, and we could also use a break. So those are also different ways you might see this algorithm implemented. Now, let's say we have a sorted list. So the linear search, including the improved one that we just looked at, can be conducted on any data. Doesn't need to be sorted. But let's say we know that our data is sorted. Well, we can actually add another condition. So now we're going to have 3 conditions in our loop condition so that we can again stop when we need to. So now we have still our condition that we assume we haven't found it, but we also assume that we're not past it. So think about this. If our list is sorted, and let's just say we have a list 1 through 10, right? And we're looking for the element 4. We look at the 1, it's not equal. Look at the 2, it's not equal. Look at the 3, it's not equal. Look at the 4, it's equal. We're done. And we'll exit because found will then be true. But now let's say we had an array of only even numbers and we're looking for the number 5. So we'll compare it to the 0, it's not equal. We'll compare it to the 2, it's not equal. We'll compare it to the 4, it's not equal. We'll compare it to the 6, it's not equal. We're never going to find it, right? Because 5 is not going to be in our array of even numbers. But remember, this is sorted. So once we hit the 6, do we need to keep looking? We don't, right? Because we've passed the place where the 5 would be if it was in the array. And so once we hit something that's bigger than that, we're done. We can jump out. We say, hey, it's not going to be there because I know my array is sorted. So now we can have this conditional that says, okay, as I'm looking through, if my target equals that object, obviously I've found it. But if my target is smaller than the object that I'm looking at now, or another way to say that is if the object that I'm looking at now is bigger than my target, then I'm past it. I've gone too far. And so now past it's going to be true, not past it's going to be false, and you're going to exit the loop. So the not found allows us to save some times through the loop once we find it, and the not past it allows us to save some times through the loop if it doesn't exist. So both of these will improve our linear search. Again, note that this one only works if your list is sorted. Okay. Now again, this is still order n. It's not more efficient from a big O perspective, but again, in the real world, it is going to be more efficient if you know in advance that you have sorted data. Now, what has to be true in addition to a list being sorted in order to use this version of linear search? Well, here we're invoking rather the equals method. We know that all objects have an equals method, but here we're invoking compare to. Not all objects have a compare to method. So in order to use this version of the linear search, your objects, their class would have to implement comparable. Now, they most likely already do because it's a sorted collection, and in order to sort, we need to be able to compare things, which means our class has to implement comparable. So if you have a sorted collection, this is most likely already the case. But just note that you wouldn't be able to do this if for some reason you didn't have the class didn't implement comparable. So those are our iterative linear searches. Let's take a look at our recursive implementation of linear search. So here we have a method that's going to return a Boolean. We have our first position to look at, our last position to look at. We have the array of data that we're looking at, and we have the target that we're looking for. So here we can say, okay, we're going to look through our array from a beginning position to an ending position. If those indices cross over, so I'm going to increment first, one at a time, one at a time, one at a time. If all of a sudden first is bigger than last, kind of think about that as I've gone off the end of the array, then that means the element's not in my collection. I'm going to return false. If at any time the target equals that data at that position, that means I found it. I can return true. If I haven't found it, so if I haven't gone off the end of the array, but I haven't yet found it, I need to look in the next position. So what we can do is we can recursively call this method, return that value, and update our parameters. Our parameters now, we're going to look at first plus 1. So if before, first was 3, 4, 5, 0, and 5 was 1, 2, 3, 4, and last was 6, and we check here, and that's not the target. Well, now we want to run that linear search method again recursively, but now we want to check this one. So we invoke it with first plus 1. Okay. Now, a couple of key things to note here is that first of all, you have to return the invocation of the recursive method. Remember, when you have valued recursive methods, you always have to return them. You should never just have that valued recursive call out there on its own, because if that's the case, you'll lose that information. So you either have to return it directly or store it to some local variable that's then going to be either updated or returned. Okay. The other thing to note is that the order of these conditionals matters. If we tried to check for equality first, and we'd gone off the end of the array, we're going to get an array index out of bounds exception. So we got to make sure that we first make sure it's a valid index. If it is, then we can see if it's what we're looking for, and if not, we keep on going. Okay. So that is linear search recursive. Now, could we also modify this to be more efficient on a sorted list? So what condition could we add in here to make it so that if we have a sorted list, we don't look more times than we need to when the element is not inside our collection and it's not in our list? So I'm not going to show you that, but think about that. Think about what change you would need to make this recursive version a little bit more efficient for sorted lists, just like we did with the iterative version. Okay, so let's take a look at some actual code.